Bismillahirrahmanirrahim. In this tutorial, I will demonstrate power in AC circuits. I begin with general impedance case, any combination of R, L, and C components. In this tutorial, we have the instantaneous voltage in blue, the instantaneous current in red, and the instantaneous power in green as shown. This is the general case where there is a shift by an angle theta between the voltage and the current. We will discuss this general case first. For each case, we vary theta by varying z. Then we obtain the instantaneous power. This is the green curve. The instantaneous power can be positive or negative. In each case, we are only concerned about the average power. The green is the result of multiplying instantaneously the value of the voltage with the value of the current, point by point. So in this case, as you can see, we have some instances of time we have positive power, and some instances of time we have some negative power. You see this small dip below zero, and on the average for this case we have a positive power. So power is absorbed in the load. Now I would demonstrate this for different phase differences between the current and the voltage. In this case, both the voltage and the current are in phase, as we see. My original voltage source in blue, sinusoid with amplitude 1. Now I will start with a current. This is the current in red. We don't care about the amplitude, so it's same amplitude. So if you multiply the current and the voltage, they are on top of each other. So the negative with the negative here is a positive, and the positive with the positive is a positive. So that's why we have double the frequency. We result in double the frequency. Now the power will come out in green, and we'll see that in this case it is all positive power. This is the case of simple resistor. It absorbs power all the time. If we have a zero voltage, it will result in zero power. For the capacitive load case, for example, a capacitor and resistor, in this case, the angle theta is positive or leading. We will see now the impact of this leading angle. Now the phase is 30 degrees, the current is shifted to the left, and the power has some power instantaneous below zero, and the average is generally positive. If we are not drawing the average value, but we can guess that it is generally positive value. Now we have increased the angle to 60 degrees. If you look, we expect that some more negative power. As you see, this is the zero reference, and we have some more negative power, and again we have on the average a positive power. Now we have a 90-degree, and this is very important case. When we have 90-degree phase difference, if you notice that the positive power equals the negative power, so there is no average DC. The average power consumed is zero, and this is the case of a capacitor, pure capacitor or pure inductor. In this case, we are talking about leading, so it's pure capacitor. Now we have increased beyond 90, so 120, we have on the average a negative power, some negative power case. Now in this case we have reversed the role of the load and the source. The load becomes a source, and this again 150-degree, we have more negative power as we expect. Look at this. On the average we have some positive, so on the average it is delivering power to the load, to the source. The load is delivering power. So this is the case of a generator. Now in this case we're talking about generators. Now we have 180-degree extreme case, and in this case we have no positive power, totally negative. So this is a case of, in this case, because we have leading current, leading power with what we call it a synchronous generator. Now we move to the inductive case. In the inductive case, the angle is negative or lagging. We will see now the impact of this lagging angle on power. Now we will move in the opposite direction. I mean, we decrease the angle by 30 degrees in each case. So this is our voltage source. I will have we start with 0 again. To remind you, we have again a positive power at double the frequency. Every time we have double the frequency, but shift in the power. So this is the case for 0-degree phase shift. We have all the time positive power, average positive power, with no negative power. It's totally consuming the energy in the load. Now we'll have a minus 30 degree. This is a minus 30 degree. Now the current looks advancing, but it is lagging behind. Now this is inductive circuit, and we start again like in the leading circuit, previous circuit. We have start a dip in the average voltage and some negative average power and some negative power. Now again we have increased the phase difference to 60 degree, and we expect again that we will have some more negative power, and still we have an average, on the average, a positive average power. And so on, we proceed to minus 90, which is equivalent, similar to the case of plus 90. Now, for the case of minus 90, the current is lagging by 90 degree. If you look at this phase of 90 degree, and in this case, again, we have a total power with average 0. I mean, the average, total average is 0, and we have an AC power at double the frequency. So this is the case of a pure inductor. Now we move to more than 90, we expect more and more negative power, and now the load and the source are somehow interchanging roles. We are having inductive circuit that is delivering to power to the source. So it's now we are talking about generator, and in this case inductive machine. So again we move to 150 angle and 180, and then finally to 180 degree. This is 150. For the case of 180 degree negative is equivalent to 180 degree positive, like total generator, I mean, in this case. Okay, so this demonstrates 4 quadrants, in fact. 0 to 90 positive, 90 to 180, and 0 to minus 90, the negative, minus 90 to 180. When we have a positive phase angle, so a positive phase angle is, so a positive phase angle when the current leads the voltage in the circuit, this is equivalent to a net circuit of R and C, and we call this leading angle. On the other hand, if we have, so this is V, this is I, we have this V and this I, so we're having a negative angle. So theta is negative. If this is plus 45, this is minus 45. So theta is negative, and in this case, this is the case of a load of a resistor and inductor. Of course, if this becomes 90 degree, we'll have 0 resistor and total, the net circuit is a capacitor. It's only a capacitor. And similarly here, if the angle becomes 90 degree, there is no resistor, and the net circuit becomes a pure inductor. In this case, we say that the circuit consumes reactive power. The reactive power is this double the frequency power that I've demonstrated a few minutes ago. Of course, the net useful power in this case is 0. The average power in this case is 0. Usually, this kind of power, we call it reactive power, because it's not really, usually it's not really doing any useful job. On the contrary, there is some current flowing in one direction, and the current flowing for some other time in the other direction, and this continues. So this is a load. This is a load on generators, load on transmission lines, to have some current going back and forth, not doing any useful job. Similarly, in the case of pure inductor, 90-degree angle, we'll have, as I demonstrated a few minutes ago, we have positive, negative, positive, negative. The same as in the case of the pure capacitor, the pure inductor. Again, we have some current going in this direction for one time, in the other direction for some other, for the half of the time, and that is again load on transmission lines, generators, so on and so forth, which is not favorable. But this is purely inductive circuit. Generally, in industry, we have more or less of this case, because most loads are inductive, like motors. That's why when we later on we'll talk about using capacitors to compensate for this reactive power, which is inductive, using an element, a capacitor element, which consumes again reactive power, but capacitive reactive power. And we will demonstrate later on that probably you have noticed that you expect that the capacitive reactive power is opposite to the inductive reactive power. Basically, the capacitor is opposite to the inductor. Current and voltage relationship, and one of them is integration, the other is differentiation, which is opposite to each other. So that's the technique that is used to correct this situation, reduce the reactive power, and try as much as possible to come to the situation where we have the voltage and the current are in phase or zero phase difference between the voltage and the current. In this case, all the power consumed is active power and no reactive power, and that's a healthy situation. But a healthy situation because all the power is used and all the currents running along the cable, the transmission lines and the cables and the generators, they generate power that is useful. Of course, this is more on the interest of power companies rather than the consumer. That's why power companies ask consumers to correct the situation to this situation as much as possible. Later on we will call that power factor correction. The power factor is the cosine of this angle, theta. So the power factor correction to make this theta 0 or as close to 0. In this case, the power factor will be as close to 1 because cosine 0 is 1. So that's for now. Thank you.